Welcome everyone to the 23rd session of Statistical Learning in Practice. Let's then get started with any questions on estimation, inference or prediction for ARMA models.
Hi, I've got a couple of questions about the theory lecture on Friday, but I'm happy to wait till like Wednesday's lecture.
Okay, I mean, let's wait and see what we get today, and then otherwise at the end of this session, maybe it's a good time as well to ask.
Sorry, I had a question for the bit just after the first bit, the second bit of code in the practical, where it says, looking at the sample autocorrelation function, does it seem that the data has been generated from an MA1 process? And in the blue, you've put, no, there is clear correlation up until lag 4. Does that, but then on the scale of when we plot the correlation function, I think it only goes up to something like 1.5 or 2. So does that just mean the fourth entry or the actual number 4?
I think it's the entry. So yeah, so what this says is that if you go, so take away this one, the very first, because that's a 0th lag. And then you've got first, second, third, and fourth. So up here, that is above the blue dotted line.
Yeah. Okay. Thank you.
Yeah. Okay.
Hi. In the algebraic form of the model, just below the point that was raised, why is the intercepts coded in that way? Is there any intuition behind it?
In the second way, or in the first, or either?
Yeah. So from right there on your cursor.
I mean, are you happy with the very first expression here that I'm selecting? So the operator, the AR operator applied to xt minus mu equal to the MA operator times the white noise. Are you happy with that one?
I suppose in lectures we had that expression without the mu.
Exactly. So what you want to do is to remove the mean from the process, and then you have a mean zero process, and you can apply the whatever expression I gave you for the zero mean process, right? And so at least this bit that I'm selecting should be making sense for that reason, right?
Yeah, that makes sense. So yeah, I suppose it's just naturally comes from removing the mean, and that's your intercepts. That's what you mean by it.
Exactly. Yeah, exactly.
Yes.
Yeah.
Hi there. I do have some questions. I've probably got.
Can I before you ask a question, please? Just for the previous one, because the person asking mentioned the intercept, and you could interpret the intercept to be precisely the product of this mu times be 1 minus pi 1. But I mean, it was only that comment. So if you had zero mean processes,
that's good. Cheers.
yeah,
That also
yeah,
makes sense.
yeah. But it's a matter of terminology. Anyway, sorry. Go ahead. Was Lenny perhaps? Yeah, there was another question, I think.
Yeah. So when we are looking at the waiting time data to start with, and we are like, well, page 89 halfway down, we're asked to give the algebraic form of the underlying model and the fitted values. So I kind of expected fitted values to mean like our predictions, as opposed to like the fitted values for the parameters. So I'm not like, yeah, just to clarify, what does the wording mean? And then I guess the follow up, if the fitted values are indeed just like the values for the parameters, then what does this kind of mean in terms of prediction?
I mean, I think this is in line with the rest of the terminology in the course, in which, you know, it was asking about the model, and then fitted values would mean the values of the parameters that have been fitted from the data. So I don't see too much confusion there arising, but because also if you were to say that these corresponded to predictions, then what prediction would they correspond to, right? I mean, it's a bit ambiguous itself. And then in terms of prediction, then you need to do, you know, what we were saying about predicting ARMA models.
Remind me, what were we saying?
So at the end of the theory, I introduced prediction from finitely many samples, and for that we needed this innovations algorithm, and which is not included in the notes, but which allows us to, I mean, so we could have predicted in ways in which I explained there in the very last section of the notes, and via the covariance matrix, some covariance, some autocovariance vector as well. And just an efficient way of doing that is via this innovations algorithm that I was saying.
Okay. So it seems to me like a very simple way one could fit make some predictions would just be to say that x hat of t is kind of this mean mu hat plus like this phi 1 x t minus 1 minus mu hat, because that would at least kind of give us some, like, that would be like the mean, assuming we knew the previous value. Is that a reasonable thing? And indeed, would that be the output from the algorithms that were in lectures?
You mean for the t, for the, say, let's say we have data from 0 to n. So you're saying that as the prediction for the n plus 1th?
Yeah.
I would be surprised if it weren't that. Yes.
Okay. Thanks.
But then when it comes to the second, n plus 2 and so on, then that's a bit. I mean, okay, yeah, no, maybe that's not the right answer. I would be surprised if the answer is too far from that. So,
Okay.
Yeah.
And then, so this is like unrelated. I'm just kind of going through a list of questions. So if anyone else has anything, please do jump in. So I'm looking at this waiting time data, and you said there was no kind of seasonality. Like, it seems to me like there's like fairly regular peaks, at least like between 1 to 3. Like, so are those just like not regular, or could you just say a little bit more about why that isn't seasonality? I mean, like,
can I just check? So you mean here from plotting this, I guess, the bit that I'm having.
yes, I think so.
You mean this bit?
No.
Big, yeah.
I think I guess I mean a bit later. I'm looking at the residuals. Sorry, so it's the bottom of the next page actually.
This. So I guess not this either.
I guess I was reading the question and then kind of overthought it and like started to imagine seeing things in the data and started to imagine that there was like some sort of regularly spaced pattern in that graph of the residuals.
Yeah, but are you sure it was this bit of a practical? Because it could have been the next. No.
I think it was that bit. ACF of weight.ar dollar residuals.
Okay, so the AR. So this one here.
Yeah.
I mean, it doesn't look to me as if there was any seasonality. I mean, I think, I guess 2 comments about seasonality. One is that, indeed, you could say that, there are some regular patterns here that go, maybe every, let's say 1, 2, 3, 4, 5, every 5, 6 elements here. It is true that we're having a peak upwards and then downwards and then upwards, downwards, and so on. But that's very well explained as well from the models that we are considering, right? Because this is just, there is just simply imagine that there isn't any dependency on more than one element, then this is just, a Gaussian that is going up and down. We're adding a new Gaussian, and so it goes up and down. Sometimes we don't notice it, like here, for instance. But then right before we do, because they were, they were a clear change of trend or direction, right? But I think seasonality is one of those that you've got to have intuition as to why there is seasonality, because if you're doing time series that are, so the usual example is time series that are a year long, and then due to actual natural sessions, like autumn, spring, and so on, then you sort of see that in the big picture. Let's imagine. So we have this picture here on the left. Now make this very wiggly in each place. You would still see this sort of big picture type of season or seasonalities, right? But when it comes to this, and you have repetition of every 4, something like that, then I would be a bit more worried, especially if you don't have any reason to believe that there should be one.
Yeah. So I guess intuitively, I thought this was so this is meant to be like call center. Is it call center data? No, waiting time. Anyhow, because these were kind of average hourly waiting times, it seemed to me reasonable that there might be some sort of daily seasonality.
Yeah.
And so I like actually looked at the sample means for each different hour and thought that I observed some sort of trend, but
yeah, I mean, if you have that sort of intuition, then you can do two things. I mean, you can try to fit a linear model as we did in the previous one, and then here the trend really is not. I don't think there would be much trend, so maybe you can even avoid that bit. But then you would need to find out what the period, repetition is, and that I find a bit hard actually here. But it's not to say that you couldn't. And then the other option is just trying to difference the series, right? So you could try to fit a KP as what, or run a KPSS test to see whether there is unit root which is causing the seasonality as well. That could be another option.
So a unit root causes seasonality?
You can, as in you can have some season-like movements when you have unit roots. Yes.
Thank you.
Yeah.
And so, I don't know. Can you see that graph there? No, this is awful, isn't it? I think I'll give up. Don't worry about that.
I think there was someone else asking.
Could I ask another little question on the model selection we do?
Yeah, of course.
So just at the end of analysing this waiting time data, we kind of compare an MA4 to an AR1 and choose the MA4 based on a CACE. So I guess it kind of seems that even though a KK gives us a like MA4 being better, it seems like a lot more complicated, and I don't know, doesn't actually seem to do a heck of a lot better on a KK or anything. Indeed, like, I don't know, I haven't actually compared the BIC, but that penalizes more for extra parameters, doesn't it? So I think it might be the other way around that. Anyhow, so I did a little experiment and thought that maybe an AR2 might be a decent thing to consider, because then you kind of have an extra parameter to play around with, but it's also like conceptually simpler, and that had like slightly better AIC than the MA4. So kind of what's the, like, is it the case that we were just comparing the AR versus the MA4 because those were like the lowest order of such models which would fit the data? And then, so I guess why is it that we kind of wanted to try just like simplest AR versus simplest MA?
Well, I think it's beyond simplest in that what we were doing is looking at the autocovariance or autocorrelation in this case functions, and so it's not here. So I think this may be, yeah, so there's the autocorrelation function for the original data, and so what this tells us is that the order, if this were coming from an MA process, then the order would be at most 4. This is what this tells us, because we have, that MA processes have lag 0 from the Q+1th element onwards, and so that's pretty much it. But it could very well be that because we have finite sample, finite data, then there is slight fluctuation here, and this guy should have been bigger. So indeed, you could be a bit cautious and try to add, maybe one more order into the models under consideration. and perhaps be surprised that that gives you a better AIC value than others. And I mean, it's exactly the same, same answer with the AR model when we look at, and rather than the autocorrelation function, we look at the partial autocorrelation function, which I would assume is here, but maybe not. Maybe in the next bit. So I wonder, no, so it should be here. No? Okay, so I guess I just fitted this without. Okay.
And so,
yeah, when it comes to, oh, I see. Okay. Yeah, okay, I see why I did an AR1. So AR1, I mean, indeed, you have this geometric decay. And with this geometric decay, you may also get things like the ones we've seen here, which is, complete, you're breaking the geometric decay, but then it sort of continues somehow. And again, as I said last time, it's not possible that you have all of the values of the sample autocorrelation function to be positive, because they need to add up to something, and indeed some have to be negative, even though of course we're not seeing here all of the possible lags, and so it could be that you see all of these to be positive because then some others are negative afterwards. But anyway, it's not surprising that this is negative, as in that's not against being an AR1. But indeed, I mean, yeah, okay. You could say, well, this maybe looks like AR1, and then just to be cautious, let's add AR4, and so you have now a set of models that you can then compare via AIC. Yeah, and that could be as well just fine. Which is a bit what you're saying, basically.
And you say we had to have these all add up to something.
Yeah.
Can you I think I probably just switched off at some point. What do they have to add up to?
No, I mean, you didn't switch off. It's coming in the 4th example sheet.
Okay.
That there is a relationship they need to satisfy, and it means that you cannot have all of them to be positive, basically. Even if the if the underlying process is AR1 with positive parameter, in which case you have this geometric decay with all of them positive, then when you have finite sample, that's not really what happens.
Okay, thanks. And then, so just like in this first part, we only compare AR versus MA, and we don't consider AR MA. Is that kind of just like for pedagogical reasons? We want to move on to doing that later.
Yeah, exactly. Yeah. I'm not doing this in the absolute best way in which you could be doing it. I mean, it's just to build up intuition and sort of introduce the concepts or kind of questions you would get.
And so now kind of moving on to the call center data, when we have this plot of like number of calls versus hours in the day.
Mm-hmm.
So one thing that struck me was this kind of looks smooth, or at least it looks a lot smoother than the previous plots we've seen in this practical. And I think I remember last practical, there was some sort of comment along the lines of something that looks a bit smooth is possibly non-stationary, and it kind of suggests it's more from an ARIMA process than an ARMA process. And I don't think we make that kind of comment here. And so I was just wondering what the difference is, or like what I'm missing.
Yeah, I mean, so we have 20 data points, as you can see here. So 20 data points is actually very few data points. So it's not surprising that we see it being regular. if we had 100 data points and this were the picture of it, then it would be a different story. So it would definitely be, I could say that it looks, smooth-ish. With 20, I don't know whether I would dare to say that this comes from any smooth process, to be honest. Because, it's just like if you wanted to, it's just like if you zoomed into one of these guys, then it would look similar to that, right? So if you zoom in off here and get, some sort of section here, then of course it's not going to look like, crazy. It's like if you start here and end here or something like this. Yeah, so then, I mean, smoothness doesn't in any way guarantee non-stationarity or stationarity. There is no relationship, but I think what I said at some point is that looking at the profile of the autocorrelation function, there were very, very high values for a number of lags, and that made me think, well, maybe if there is such high dependence between values of different order, at different times, consistently as you move, then this may mean, smoothness, and this smoothness, if it is very strong, then it seems strange that you could keep the first two order properties constant in time. But to be honest, thinking about it now again, I'm not sure one can conclude that either. So, I mean, I was being cautious, but and I was rightly so being cautious, because I'm not sure it would really mean lack of stationarity. I mean, I'm sure we can work out an example in which we have that autocorrelation function.
Actually.
Yeah, say it again.
If you have something like a sinusoid with random phase.
Yeah. 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 So yeah. I mean, I was saying that just to give intuition as to what the meaning of that autocorrelation function would be in terms of this dependency and this smoothness, but yeah, it's very hard because it's only a diagnostic plot and it's actually a very limited one, this autocorrelation function. So this is why it's good also just to fix. I guess is why it's good to fix the criteria, the selection criteria beforehand, before using the data, right? Because now you say, well, MA4 is too complex, so actually VAC may be a bit better. But then you're deciding that after you've seen the data and after you've fitted the data, and that's a bit dangerous.
And so I guess what I think is probably my final question is kind of related, which is I don't think we actually fit any ARIMA models to this. Or maybe we do.
I don't. I think maybe we don't, because the KPSS test negative.
Okay, so we're using this auto ARIMA thing function, and it observes the KPSS isn't telling us that things are significant, so we don't bother. So the automatic thing doesn't take us to a D=1 case.
Yeah, but
there's no reason why we should consider it if that's the case.
Even before that, at the bottom of page 91.
Oh yes.
We do KPSS test, and it says no at 10% level.
Yeah.
And so no, so we completely rule out the possibility. And then we confirm this yet again in this automatic fitting.
Yeah. Okay, great. Actually, on that subject, I couldn't really work out what the output from the KPSS thing was. Like one of the things that output was KPSS level, Do you know what that was?
Do you mean here in the very first or the later?
I think that. Yeah, I think that. Yeah.
I think isn't this is just the value of the test statistic, no?
Okay, that would make sense. Yeah.
Yeah.
And truncation lag parameter.
Okay. So there are two options here. Let me just think. That's a bit strange. Yes, this would mean. Not sure I want to answer what I want to answer. Because it could be that. So what I'm thinking here is yeah, what I'm thinking here is that some definition of one of these that goes all the way to it shouldn't be. Yeah, I'm not very sure actually. I don't know whether this refers to the Newey West estimator for the sigma squared, in which case maybe it has some sort of lag parameter that you need to play with, or whether it applies to something internal of the computation of the t statistic, the statistic. Because in the statistics, at least the one I gave you, I can't see any issues with choosing lags in any way. So you're right. I missed this as the meaning of that. I can look it up for Wednesday.
I guess yes, please. Sorry,
Sure.
we're getting down a rabbit hole here. What is the Newey West estimator? Is that like just the name for one of the things which we came across in lectures?
I don't know by that name whether it is the one we're using or something different.
Okay. Further research needed. Great. Thanks.
Sure.
I think I'm done for now. So.
Okay.
We'll mute.
Right. Any more questions?
A question about the intercept. I remember a previous question. You mentioned that the intercept is related to the sample mean, and I found that for weight data, the MA4 and the AR1 model have different intercept, but they use the same sample. So I was thinking whether they have a different. Is that arise from the two models have different account for randomness, or why they are different?
Just Just give me a sec. Let's see. I mean, they could well have a different mean parameter, yes. And it's not, yeah, I mean, I guess what you're saying in a way is what's going on, which is that they account for randomness in a different way. Because imagine, so forget about an intercept or a mean. So just imagine that you're considering an AR1 and MA4 processes that have zero mean, then they will look quite different, right? In the pictures, or at least, if you run them for some time, you will be able to spot out differences between them. And so now, if you have a data set, you have the trajectory of a time series that you want to fit a model to, then of course, if you wish to fit an MA4 model or an AR1 model to that data, then of course the parameters are going to have to adapt a bit differently to explain that variability via one or the other model. And so of course that could give different values of the mean and actually of any other parameter that they may share. Right?
Yeah. And can we just center the data before do the test, or is and which way do you think better? We center the data first, or we use a model with intercept, or because they may have slightly different.
Yeah. So this is a matter of whether you want to use like a least squares estimator or a likelihood estimator, right? So you could, if you believe that there is stationarity, then why not to just fit a linear model and try to remove the mean out of it? Yeah. So that's one possibility, and that's like a least squares estimator. Or just fully trust your distributional level assumption, and from that you're going to get an MLE basically from the rest of things that you're doing.
Okay.
So it's a matter of taste of whether you want to go fully MLE, or you wish to also use an estimator that doesn't even require you to have this Gaussianity, which is the least squares. So least squares doesn't really require Gaussianity to be built, right? To gain intuition on it. But indeed, they may give you slightly different values, yes.
Yeah, okay. Thank you. And my other question is just about curiosity, because it's in the, let me see the practical. In the in page 93, using the auto ARIMA fitting the model, and the explanation about this, the outcome says the ARIMA models, we will select all models with PQ parameters up to 5, and I found the result report don't have any PQ that's larger than 4 or 5, and is that they just decide to stop at some point, or they're just satisfying with PQ is 1 or 2 or 0, or it's curiosity. Will they actually trial over all PQ smaller than 5, or they can stop, or?
Yes, what is going on here is that you're doing this let me see. I mean, this should be going via a greedy search. It is stepwise greedy search. And so at some point, what would be happening is that you try out a model that has higher values of the parameters, of the order parameters, and then that tests, well, it doesn't test, but it gives you a lower, a larger AIC value, and so you don't go beyond that. You just stop here, basically.
Oh, okay. Yeah, is this or see okay, yeah, because I thought like they're just like a trial over some PQ, and it's not that guarantee that PQ is larger than the AIC is larger, or they may have some problems. Model, so I was a little bit confused, but maybe for parsimonious, it's better to keep PQ small. Yeah. Okay, thank you. Yeah, I think, yeah, I understand.
Yeah. Yeah, I think the question here is whether the greedy search is also including part of the elements that it was going back through. I don't know in what exact order this is doing the search. Where it is starting from, whether it is also starting from different models. Sometimes.
You can get it to check all values up to 5 if you set the parameter stepwise equals false. Really cool.
Right. So you can definitely, exactly, have an exhaustive search if you do that. Then see what happens there.
Okay.
Actually, I say that I did it, and it's giving me some weird subsection. I think it's taking all values with p plus q less than or equal to 5.
Okay.
Right. So here there are some of them with the 5. Yes. Yeah, but there is something that is a bit unsatisfactory here, I think. Wait a second. Yeah, okay, so there is this maximum order. I think this may be the sum of the two orders. And so even though P and Q have been set to 5, the maximum order is the sum of these two in the case of armor modes. And so this is why the sum is never going up to anything that is more than 5, and in this one, the sum is not. You don't really get more than 5 parameters in here either.
Yeah, thank you.
Yeah, And so the greedy search actually stops earlier than the exhaustive search, as you see.
Oh, yeah. Cool. Thank you.
Like a stupid question for interest based on the documentation. I don't know whether you've dug into it. Oh yeah, there. You've got the start dot capital P and start dot capital Q. As unlike there's these capital P's and capital Q's as well. There's the little P's and little Q's. Do you know off the top of your head what those are?
I'm just thinking whether they have to do with ARIMA before differentiation. That's the only thing I can think of, but no, I mean, I wouldn't dare to give you an answer because I don't know it. So there's seasonal differences. Oh, sorry, you were talking about the P and the Q, yes. Yeah, I'm not sure, to be honest. Let's see. By the way, I just remembered. So I got a question on the last practical on how to model this, because we were sort of jumping ahead a bit as to how to fit a model to the residuals here, and I said that there was a clear change here of sort of behavior, which I think there is, around 30. You could try to fit two different models there, but then I realized that as well as that, you could see that the activity is somehow growing in time. So you see more and more as you increase time. And that can also, I've just been reminded by this, because it does say here, there are some Box-Cox transformations. And you could apply some Box-Cox transformation to this as well. So say you could take, the logarithm of the absolute value and then time that with the sign of the element that you were considering. And when you do that, this will be shrunk, this area in comparison to this area that will be. And so they will be at the same sort of level of fluctuation, right? And so there now it would make sense to try to fit some ARMA model. So those are perfectly normal things as well, just do transformations. So, I mean, we saw that in statistical modeling that you can try to do these Box-Cox transformations, but then that's one thing. And then the other is just trying to find a more appropriate model straight away for it. That allows you to have more control over the resulting, first and second order properties of the resulting model. But here, as a first thing to try, you could definitely try that. Okay, any more questions or someone who wanted to ask about the notes?
Oh yeah, thanks. There were three things I had. And the first two were to do with like discrepancies between the ones you uploaded, the theory notes, and then like what you wrote down in the lecture.
Okay.
In a couple of places. So the first one was, let's find it. When you started describing, I guess, like the stuff around the innovations algorithm, and you in your like written notes, you could find this thing called xn hat, and then you used it to find this like ut. But in your printed notes, you called it x. You called them an xt hat.
That would be, I guess, here. So, I mean, so you have the x hat being just the expectation, the conditional expectation, and then the u is the difference between them. So I don't know what I wrote in the iPad.
Oh, no, so it's xt hat rather than xn hat for like each of them.
Yeah, I mean, it depends on what I was trying to write, but if t is a variable, then yes, it would be t rather than n, unless I was trying to write it for some reason for the nth, for t equal n for a given reason that I ignore because I don't. Let's see. So where was that? So it would have been xn. Yeah, no, that surely that's xt. Yes, you're right. Yeah. This is xt, next t. Yeah, both sides. And here as well, yeah. Actually, I guess I was being very consistent to make it the n everywhere. But no, but they should all be t, yes.
And then in the definition of S, of capital S, I think a couple of lines down, there's also a slight inconsistency. I think in your printed ones, you had divided by R of T.
And it could be.
In your
it depends.
You had like
I guess it depends on how I phrased it. But yeah, here it shouldn't have VT but RT because the sigma we already plugged in the value here. And here it wouldn't make sense either. Yeah, so this should be an RT, yes. Rather than VT minus 1.
Yeah. And the last question I had was actually, it's the same in both of them. So it was more just me maybe being a bit confused. But when you defined your A vector in the forecasting section, as you kind of differentiated it, and I tried differentiating it, and I got it as being that, but the kind of gamma vector as being kind of the other way around. So like the first term in the gamma vector being the h plus n minus 1.
Could that be? Let me just. I mean, it can be. Let me just think about it. It could be. Could be. Okay, I'll double check that for Wednesday. But yeah, it could be. There's that. Yes.
Thanks.
Sure. Because I mean, I haven't done this calculation this year, so it could well be a typo from last year, and then I just haven't realized.
And just to clarify, I didn't quite track those two comments just there. Is it the case that the type notes are like correct in both cases, and what was lectured that had a couple of slips in it? So I can just like go through the notes and check.
All the way around. So there were some typos in the handwritten notes.
Yeah.
That are correct in the notes. Yeah. So I don't know if that's what you said, but yeah.
I can't English sometimes.
Well, maybe it's me. But anyway, yeah. So this bottom of page 51 in the notes.
Thanks.
And actually just a bit after as well. So all of that bit.
Great. Thank you. I'll go through that. I've got to dash. Thank you so much. Bye.
Okay. Thank you. Bye. And I think if there is any pressing question, then I can take it. Otherwise, we'll close it here as well. Okay, then. So I'll see you on Wednesday when I remind you that we'll basically have a Q&A session, and I owe you answers to a few things. So I will also give those because I think they are of interest to everyone. So thank you for your attention, and see you again on Wednesday. And we don't have an office hour on Wednesday, by the way. Okay, bye now.